Fault-Tolerant Consensus. Informally, consensus means getting several nodes to agree on something. For example, if several people concurrently try to book the last seat on an airplane, or the same seat in a theater, or try to register an account with the same username, then a consensus algorithm could be used to determine which one of these mutually incompatible operations should be the winner. The consensus problem is normally formalized as follows. One or more nodes may propose values, and the consensus algorithm decides on one of those values. In the seat booking example, when several customers are concurrently trying to buy the last seat, each node handling a customer request may propose the ID of the customer it is serving, and the decision indicates which one of those customers got the seat Roman 13. This particular variant of consensus is called uniform consensus, which is equivalent to regular consensus in asynchronous systems with unreliable failure detectors. The academic literature usually refers to processes rather than nodes, but we use nodes here for consistency with the rest of this book. In this formalism, a consensus algorithm must satisfy the following properties: Roman 13 uniform agreement, no two nodes decide differently. Integrity, no node decides twice. Validity, if a node decides value v, then v was proposed by some node. Termination, every node that does not crash eventually decides some value. The uniform agreement and integrity properties define the core idea of consensus. Everyone decides on the same outcome, and once you have decided, you cannot change your mind. The validity property exists mostly to rule out trivial solutions. For example, you could have an algorithm that always decides null, no matter what was proposed. This algorithm would satisfy the agreement and integrity properties, but not the validity property. If you don't care about fault tolerance, then satisfying the first three properties is easy. You can just hardcode one node to be the dictator, and let that node make all of the decisions. However, if that one node fails, then the system can no longer make any decisions. This is, in fact, what we saw in the case of two-phase commit. If the coordinator fails, in-doubt participants cannot decide whether to commit or abort. The termination property formalizes the idea of fault tolerance. It essentially says that a consensus algorithm cannot simply sit around and do nothing forever. In other words, it must make progress. Even if some nodes fail, the other nodes must still reach a decision. Termination is a liveness property, whereas the other three are safety properties. See safety and liveness on page 308. The system model of consensus assumes that when a node crashes, it suddenly disappears and never comes back. Instead of a software crash, imagine that there is an earthquake, and the data center containing your node is destroyed by a landslide. You must assume that your node is buried under 30 feet of mud and is never going to come back online. In this system model, any algorithm that has to wait for a node to recover is not going to be able to satisfy the termination property. In particular, 2PC does not meet the requirements for termination. Of course, if all nodes crash and none of them are running, then it is not possible for any algorithm to decide anything. There is a limit to the number of failures that an algorithm can tolerate. In fact, it can be proved that any consensus algorithm requires at least a majority of nodes to be functioning correctly in order to assure termination. That majority can safely form a quorum. See quorums for reading and writing on page 179. Thus, the termination property is subject to the assumption that fewer than half of the nodes are crashed or unreachable. However, most implementations of consensus ensure that the safety properties agreement, integrity, and validity are always met, even if a majority of nodes fail or there is a severe network problem. Thus, a large-scale outage can stop the system from being able to process requests, but it cannot corrupt the consensus system by causing it to make invalid decisions. Most consensus algorithms assume that there are no Byzantine faults, as discussed in Byzantine faults on page 304. That is, if a node does not correctly follow the protocol, for example, if it sends contradictory messages to different nodes, it may break the safety properties of the protocol. It is possible to make consensus robust against Byzantine faults as long as fewer than 1/3 of the nodes are Byzantine faulty, but we don't have space to discuss those algorithms in detail in this book. Consensus algorithms and total order broadcast. The best-known fault-tolerant consensus algorithms are view-stamped replication via Hasar, Paxos, Raft, and Zab. There are quite a few similarities between these algorithms, but they are not the same. In this book we won't go into full details of the different algorithms. It's sufficient to be aware of some of the high-level ideas that they have in common. Unless you're implementing a consensus system yourself, which is probably not advisable, it's hard. Most of these algorithms actually don't directly use the formal model described here, proposing and deciding on a single value, while satisfying the agreement, integrity, validity, and termination properties. Instead, they decide on a sequence of values, which makes them total order broadcast algorithms. As discussed previously in this chapter, see total order broadcasts on page 348. Remember that total order broadcast requires messages to be delivered exactly once, in the same order, to all nodes. If you think about it, this is equivalent to performing several rounds of consensus. In each round, nodes propose the message that they want to send next, and then decide on the next message to be delivered in the total order. So, total order broadcast is equivalent to repeated rounds of consensus, each consensus decision corresponding to one message delivery. Due to the agreement property of consensus, all nodes decide to deliver the same messages in the same order. Due to the integrity property, messages are not duplicated. Due to the validity property, messages are not corrupted and not fabricated out of thin air. Due to the termination property, messages are not lost. View-stamped replication, Raft, and ZAB implement total order broadcast directly, because that is more efficient than doing repeated rounds of one value at a time consensus. In the case of Paxos, this optimization is known as multi-Paxos. In Chapter 5 we discussed single-leader replication, see leaders and followers on page 152, which takes all the writes to the leader and applies them to the followers in the same order, thus keeping replicas up to date. Isn't this essentially total order broadcast? How come we didn't have to worry about consensus in Chapter 5? The answer comes down to how the leader is chosen. If the leader is manually chosen and configured by the humans in your operations team, you essentially have a consensus algorithm of the dictatorial variety. Only one node is allowed to accept writes, i.e. make decisions about the order of writes in the replication log. And if that node goes down, the system becomes unavailable for writes until the operators manually configure a different node to be the leader. Such a system can work well in practice, but it does not satisfy the termination property of consensus because it requires human intervention in order to make progress. Some databases perform automatic leader election and failover, promoting a follower to be the new leader if the old leader fails. See handling node outages on page 156. This brings us closer to fault-tolerant total order broadcast, and thus to solving consensus. However, there is a problem. We previously discussed the problem of split brain, and said that all nodes need to agree who the leader is, otherwise two different nodes could each believe themselves to be the leader, and consequently get the database into an inconsistent state. Thus, we need consensus in order to elect a leader. But if the consensus algorithms described here are actually total order broadcast algorithms, and total order broadcast is like single leader replication, and single leader replication requires a leader, then it seems that in order to elect a leader, we first need a leader. In order to solve consensus, we must first solve consensus. How do we break out of this conundrum? All of the consensus protocols discussed so far internally use a leader in some form or another, but they don't guarantee that the leader is unique. Instead, they can make a weaker guarantee. The protocols define an epoch number called the ballot number in Paxos, view number in view-stamped replication, and term number in Raft, and guarantee that within each epoch, the leader is unique. Every time the current leader is thought to be dead, a vote is started among the nodes to elect a new leader. This election is given an incremented epoch number, and thus epoch numbers are totally ordered and monotonically increasing. If there is a conflict between two different leaders in two different epochs, perhaps because the previous leader actually wasn't dead after all, then the leader with the higher epoch number prevails. Before a leader is allowed to decide anything, it must first check that there isn't some other leader with a higher epoch number which might take a conflicting decision. How does a leader know that it hasn't been ousted by another node? Recall the truth is defined by the majority on page 300. A node cannot necessarily trust its own judgment. Just because a node thinks that it is the leader, that does not necessarily mean the other nodes accept it as their leader. Instead, it must collect votes from a quorum of nodes. See quorums for reading and writing on page 179. For every decision that a leader wants to make, it must send the proposed value to the other nodes, and wait for a quorum of nodes to respond in favor of the proposal. The quorum typically, but not always, consists of a majority of nodes. A node votes in favor of a proposal only if it is not aware of any other leader with a higher epoch. Thus, we have two rounds of voting, once to choose a leader, and a second time to vote on a leader's proposal. The key insight is that the quorums for those two votes must overlap. If a vote on a proposal succeeds, at least one of the nodes that voted for it must have also participated in the most recent leader election. Thus, if the vote on a proposal does not reveal any higher numbered epoch, the current leader can conclude that no leader election with a higher epoch number has happened, and therefore be sure that it still holds the leadership. It can then safely decide the proposed value. This voting process looks superficially similar to two-phase commit. The biggest differences are that in 2PC the coordinator is not elected, and that fault-tolerant consensus algorithms only require votes from a majority of nodes, whereas 2PC requires a yes vote from every participant. Moreover, consensus algorithms define a recovery process by which nodes can get into a consistent state after a new leader is elected, ensuring that the safety properties are always met. These differences are key to the correctness and fault tolerance of a consensus algorithm. Consensus algorithms are a huge breakthrough for distributed systems. They bring concrete safety properties agreement, integrity, and validity to systems where everything else is uncertain, and they nevertheless remain fault-tolerant, able to make progress as long as a majority of nodes are working and reachable. They provide total order broadcast, and therefore they can also implement linearizable atomic operations in a fault-tolerant way. See implementing linearizable storage using total order broadcast on page 350. Nevertheless, they are not used everywhere because the benefits come at a cost. The process by which nodes vote on proposals before they are decided is a kind of synchronous replication. As discussed in synchronous versus asynchronous replication on page 153, databases are often configured to use asynchronous replication. In this configuration, some committed data can potentially be lost on failover, but many people choose to accept this risk for the sake of better performance. Consensus systems always require a strict majority to operate. This means you need a minimum of 3 nodes in order to tolerate one failure. The remaining 2 out of 3 form a majority, or a minimum of 5 nodes to tolerate 2 failures. The remaining 3 out of 5 form a majority. If a network failure cuts off some nodes from the rest, only the majority portion of the network can make progress, and the rest is blocked. See also the cost of linearizability on page 335. Most consensus algorithms assume a fixed set of nodes that participate in voting, which means that you can't just add or remove nodes in the cluster. Dynamic membership extensions to consensus algorithms allow the set of nodes in the cluster to change over time, but they are much less well understood than static membership algorithms. Consensus systems generally rely on timeouts to detect failed nodes. In environments with highly variable network delays, especially geographically distributed systems, it often happens that a node falsely believes the leader to have failed due to a transient network issue. Although this error does not harm the safety properties, frequent leader elections result in terrible performance because the system can end up spending more time choosing a leader than doing any useful work. Sometimes, consensus algorithms are particularly sensitive to network problems. For example, Raft has been shown to have unpleasant edge cases if the entire network is working correctly except for one particular network link that is consistently unreliable. Raft can get into situations where leadership continually bounces between 2 nodes, or the current leader is continually forced to resign, so the system effectively never makes progress. Other consensus algorithms have similar problems, and designing algorithms that are more robust to unreliable networks is still an open research problem.